All right, continuing with Chapter 8, Rational Functions. Today we are going to be graphing rational functions. So just a few major steps here for graphing rational functions. You want to find and plot the x and y intercepts. You want to find and plot the asymptotes. And to show how a graph behaves near a vertical asymptote, we need to plot a point to its left and to its right. And then to show how a graph behaves near a horizontal asymptote, we need to plot points with large enough x values, both positive and negative, to show how the graph flattens out. All right, so we'll be doing that in the examples. So here, the first example, they want us to sketch the graph of this rational function. So first up, we'll do the y-intercept. And recall that is when x equals 0. So just plug in 0 wherever you see an x. 2 times 0 plus 1. And 0 minus 4 in the denominator. Anything times 0 is just 0. Here's a 0. And 1 divided by negative 4 is negative 1/4. Now for the x-intercept, that is when the denominator equals 0. I'm sorry, mistake. That is when the numerator equals 0. All right, so 2x plus 1 equals 0. Minus 1 on both sides. And the opposite of times 2 is divided by 2. So that is your x-intercept. Now for the vertical asymptote, that is when the denominator equals 0. So if x minus 4 equals 0, if you do plus 4 on both sides, x is just 4. Okay, finally, for the horizontal asymptote, let's look at the notes. All right, for the horizontal asymptote, remember we had 3 cases. If the degree of the numerator is greater, there's no horizontal asymptote. If the degree of the denominator is greater, the horizontal asymptote is y equals 0. If the degrees are equal, you just take the coefficient, the leading coefficient in the numerator and denominator, and make it a fraction. So here's our function. All right, the exponent here is just 1, and the exponent here is just 1. So the degree of the numerator and denominator are equal. The coefficient in front of the x, of course, that's just 1. Okay, so taking the leading coefficients, we just have 2 divided by 1 for the horizontal asymptote. All right, so the vertical is x equals, the horizontal is y equals, and 2 divided by 1, of course, that's just y equals 2. All right, so let's put the points on intercepts on the graph and the asymptotes. On the y-axis, negative 1/4, x-axis, negative 1/2. All right, on the y-axis, which is the up-down axis, we said negative 1/4. So that's a little bit difficult. We have to go 1/4 of the way down. That's about right there. And on the x-axis, we said negative 1/2, so it's in between 0 and 1. All right. The asymptotes are at x equals 4 and y equals 2. All right, x equals 4 is right here. So it's going to go right through x equals 4. And y equals 2. It's going to go right through here. All right, so really, we need to plot some points here because we only have 2 asymptotes and 2 points. All right, once again, for the vertical asymptote, we need to plot a point to its left and right. For the horizontal asymptote, we need to plot points with large enough x values, both positive and negative. So we're going to do both of these. So here's the original function. Let's get some x and y values. Here is the vertical asymptote. Let's plot a point to the left and right. So the asymptote's at 4. Let's try x equals 3 and x equals 5. All right, if we plug in x equals 3, 2 times 3 is 6 plus 1 is 7. And 3 minus 4 is negative 1. 7 divided by negative 1 is negative 7. And for the 5, we have 2 times 5 plus 1, that's 11. Divided by 5 minus 4, that's 1, so that's just 11. Okay, so 3, comma, negative 7. All right, let's go to x equals 3 and y equals negative 7 right there. Okay, and x equals 5, y equals 11. So let's see, here's x equals 5. And the graph only goes up to 8. So at the 5, here's 8. The 11 would be like way up here. All right. So let's see what we have. All right, this is a tough one. Let's plot large values of x for the horizontal asymptote like they said. Let's see. Let's try to do x equals 8. Okay, let's see what happens there. If x equals 8, it's off the graph a little bit. We'd have 16 plus 1, that's 17, divided by 8 minus 4, which is 4. So 17 fourths, that is the same as 4 1/4. All right, so if it were over here off the graph, this would be about x equals 8. And that would be about right here, 4 1/4. All right, so we can kind of see what the graph is doing here. Remember that the graph is going to approach the asymptotes. So for this one here, I'm thinking it's something like this. All right, because it's going to have to approach this asymptote here. In fact, this is probably a more sharp turn like so. Let me fix that. Remember, the graph is supposed to approach the asymptote. So it's probably more like that. And it's going to approach this dashed line right here. This graph, there's not enough room. I would have to rescale it to draw it properly. All right, and on the other side, let's plot a high negative, or should I say a low negative value of x. Let's try negative 6 and see what happens. All right, for negative 6, we would have negative 12 plus 1, that's negative 11. And we'd have negative 6 minus 4, that's negative 10. So that's basically 1 1/10. And that's at negative 6. All right, so at negative 6, it's going to be 1 1/10, a tiny bit above the 1. All right, one mistake I made, we said the x-intercept was negative 1/2. I put it at positive 1/2. Okay, so that x-intercept needs to be at negative 1/2. And let's see, I think I have enough here. Remember, the graph approaches the asymptote, so it's basically going through there and then right down through there. All right, it's going to approach that asymptote, but never reach it. Okay, so it gets closer and closer to the dashed line, which is the asymptote, and the same thing for the horizontal one. Okay, it just gets closer and closer to that line, but it never reaches it. All right, so this one here is a little better. This one here, I'd have to stretch the graph out much further, but just try to imagine that this curve is approaching the dashed line. All right, and down here it's also going to be approaching the dashed line. So hard to do it on this graph that only goes up to 6. We'd have to go into greater numbers, but that's basically it right there. Of x equals 1 over x squared plus 1. All right, for the y-intercept, you plug in x equals 0. That's going to be 1 over 0 squared plus 1. 1 over 1 is just 1. And for the x-intercept, we set the numerator equal to 0. Can 1 ever equal 0? Never. Okay, 1 will never equal 0. And so for the x-intercept, there is none. For the vertical asymptote, denominator equals 0. All right, x squared plus 1 equals 0. Do minus 1 on both sides. And this is going to be an imaginary number. Okay, you can't plot an imaginary number on the real axis. So for the vertical asymptote, this can never be true. So for the vertical asymptote, there's none. And then finally, the horizontal asymptote, the degree of the denominator is greater than the degree of the numerator. We can look at the notes, but just think about it. As x gets bigger and bigger, the denominator gets bigger and bigger, and you get 1 over a big, big number, and that fraction just approaches 0. If the denominator keeps getting bigger and 1 is in the numerator, this whole thing approaches 0. Okay, so the horizontal asymptote is y equals 0. If you don't believe me, just check the notes. When the degree of the denominator is larger, it's going to be y equals 0. So we don't have too much here. It looks like we're going to have to plot points for the most part. Okay, the y-intercept is 1, horizontal asymptote is 0. All right, y-axis, y-intercept is at 1. And the horizontal asymptote is basically the x-axis, y equals 0. All right, let me see if I could do it in a different color here. On the axis here. All right, so we got 1 point and we got an asymptote. So it looks like we're going to have to plot. Remember, for the vertical asymptote, you plot points around the vertical asymptote. For the horizontal asymptote, it looks like we're going to have to plot points to the right and to the left. Okay, this is the only point we have so far. So let's go to the right and to the left of x equals 0. All right, how about a table this time? Let's do x and y, because we need a few points here. All right, so let's see. Oh, wrong problem. All right, so at x equals 1, we have 1 divided by 1 plus 1. That's going to be 1/2. All right, so at x equals 1, that's going to be 1/2. At x equals 2, 1 divided by 2 squared plus 1, that's going to be 1/5. So at x equals 2, it's 1/5. All right, one more. X equals 3. 1 over 9 plus 1 is 10. So it's 1/10. All right. And how about for the negative x's? Isn't it going to be the same thing? Because you have x squared right here. All right, so if you do -1, -2, and -3, and you square it, it's going to be the same thing. All right, for instance, -1 is going to be 1 over 1 plus 1, which is 2. So that's 1/2, 1/5, and 1/10. All right, so as x gets larger, y gets closer to 0. All right, as x goes to infinity, y goes to 0. And as x goes to negative infinity, again, the y just goes to 0. All right, so that's what we're looking at. We said at 1 it was 1/2, and at -1 it's 1/2. So let's do these two. All right, at x equals 1, we said it was 1/2. And at x equals -1, we said it was 1/2. And we said as x got larger and larger, the y just gets closer and closer to 0. All right, so it just goes like that, closer and closer. And then on the other side, it's the same thing. Remember, it was x squared, so you square the x's, and it's going to be the same thing. So it just gets closer and closer to 0, but never meets it. All right, again, it would have been better if I changed the scale of this graph, like if the 1 was up here, and then we made it like, if the 1 was here, and then we made it 3/4, 1/2, 1/4, it might have been a little bit better. Okay, but that's your graph right there. All right, one more for now. Let's do the y-intercept. All right, that means x equals 0, so we have 0 plus 1 divided by 0 minus 1. 1 over -1 is -1. And for the x-intercept, numerator equals 0, x squared plus 1 equals 0. Minus 1 on both sides, you get x squared equals -1. That can never work unless it's imaginary. So for the x-intercept, there is none. Vertical asymptote, the denominator equals 0. Okay, x squared minus 1 equals 0. Plus 1 on both sides, we have x squared is +1. Taking the square root. All right, square root on both sides. Square root of x squared is x. Square root of 1 is 1. But when you do square root on both sides, you need to do plus minus. Okay, so the vertical asymptote, there's two of them. X equals 1. X equals -1. All right, and finally, the horizontal asymptote. Let's see what we have here. The degree of the numerator is equal to the degree of the denominator. So we make the fraction. The coefficient here is just 1. The coefficient here is just 1. 1 divided by 1 is just 1. So the horizontal asymptote is y equals 1. All right, because the vertical asymptote is always x equals. All right, so let's plot these points here in asymptotes. Let's go to the y-axis and put on the y-intercept, -1. All right, y-axis right here. Let's go to -1 right there. All right, we said the x asymptotes are at 1 and -1. So let's draw in that dashed line right there for x equals 1 and and negative 1. And horizontal asymptote at y equals 1. All right, y-axis, y equals 1. So let's do the horizontal asymptote. All right, interesting pattern we have here. So let me write the function here. I believe it was x squared plus 1 divided by x squared minus 1. All right, so we said for the vertical asymptotes, you want points on the left and right. We already have x equals 0. All right, I'll do the points in a different color. We already have x equals 0. Let's try x equals 2 and negative 2. All right. So let's see, I'll do a little table again. I think maybe that's better. At x equals 2, we got 4 plus 1 is 5, divided by 4 minus 1, that's 3, so that's going to be 5/3. All right, and since x is squared on both of them, if we did negative 2 and you squared it, it's still going to be 5/3. All right, so 5/3 equals 1 2/3, right? All right, that's a little difficult to plot, but we could do it. So at 2 and negative 2, y is 1 2/3. All right, at 2, we're going to go to 1 2/3. And at negative 2, 1 2/3. Okay, so we got those, and let's see. How does this approach x? I'm pretty sure it's going to be like this. Let's plot x equals 6. I'm pretty sure it's just going to approach the asymptote right there. All right, this is a little messy. At x equals 6, 36 plus 1, that's 37. 36 minus 1, that's 35. 37 over 35, it's approximately 1. Okay, and of course, negative 6 is going to be the same thing. It's just getting closer and closer to 1. It's approximately 1, but not quite. All right, so at the 6, it's right there. And at the negative 6, it's right there. It's getting closer and closer to y equals 1. All right, and I'm pretty sure this part right here is going to approach infinity. All right, let's see. If the graph, look, if the graph goes like this on this side, over here, it's going to have to approach this asymptote. So you can plug in like negative 1.1 or something. But it's already obvious the graph is going like this. All right, because it's never going to reach the asymptote. That's the point of the asymptote. Same thing on the other side. All right, you can plug in 1.1 or something and get the point way up here, but we can already see what it's doing. All right, a little crooked, but that's what it's doing. It's approaching the asymptote. And now, we only need the middle part. All right, we need the part in here. So we got this negative 1. I'm almost positive it's going to go down, but let's see. Let's plug in 1/2 and negative 1/2 for the x's. All right, let's try that. A little messy here. All right, I'm gonna do 0.5 and negative 0.5. Okay, I'm gonna do this on the calculator right here. Actually, I don't need to. 1/2. If you do 1/2 squared, that's going to be 1/4 plus 1. 1/2 squared again, that's 1/4 minus 1. So that's going to be 5/4 divided by -3/4. All right, keep, change, flip. I'm going to flip this. So times 4 over -3. These cancels. It's going to be -5/3, which is the same as -1 2/3. And of course, the negative version of that, because it's squared, it's the same thing. It's going to be -5/3 or -1 2/3. All right. So forget I said 0.5. We didn't even need to do decimal. All right. So that's going to be at 1/2 and -1/2. All right. So at 1/2, it's -1 2/3. All right. At 1/2, it's -1 2/3. At x equals -1/2, it's the same thing. So we can keep plotting points, but you can see what the graph is doing. All right, you can plot another point, but you're going to get into fractions and decimals. We can see the graph goes like this. Does it ever reach the asymptote? No, that is the point of the asymptote. The graph never reaches it. All right, so it's basically like that. All right, so we got this part, and we got those two parts. All right, it got a little messy, but that's basically it right there. All right, so moving on, we're going to be covering functions with a slant asymptote. So, for a rational function, if the degree of the numerator is exactly 1 more than the degree of the denominator, the function has a slant asymptote. To find the slant asymptote, you use polynomial division and ignore the remainder. So does this change anything that we learned previously? No, it does not. These are horizontal asymptotes, and we said if the degree of the numerator is greater than the degree of the denominator, then there's no horizontal asymptote. Okay, but there could be a slant asymptote. All right, first example, find an equation for the slant asymptote. So let's make sure that there actually is a slant asymptote. We see that the degree of the numerator, the highest exponent, is 2. And right here, the degree of the denominator, the highest exponent, is 1. So notice the degree of the numerator is exactly 1 more than the degree of the denominator. The 2 is 1 more than 1. All right, so let's just use basic polynomial division. We can actually use synthetic division on this one. Okay, remember, if you're dividing by x plus 2, you're going to use -2. All right, so I'm just going to use synthetic division here. And make sure the exponents count down by 1. Use the coefficients 4, 3, and -5. All right, make the bracket to accommodate 2 rows. Bring down the 4. -2 times 4 is -8. Adding vertically, 3 minus 8 is -5. And -2 times -5 is 10. -5 plus 10 is 5. Okay, we're probably just going to ignore the remainder. And remember, when you use synthetic division, the exponent on the answer is 1 less than the greatest exponent in the numerator. So if the exponent here is a 2, the exponent here is just a 1. So it's 4x to the 1, or just 4x, then -5 with no x, and we're just going to ignore the remainder. All right, so this right here is your slant asymptote. The equation for the asymptote is y equals that number. All right, so like I said in the notes, you just use polynomial division, or you can do long division or synthetic division. Whatever you get, that is your slant asymptote, and you just ignore the remainder. Okay, next example, we see once again the degree of the numerator is a 3, the degree of the denominator is a 2. So the numerator is exactly 1 more than the denominator, so that's going to be a slant asymptote. Okay, so we need to use polynomial division, and we cannot use synthetic division. So let's write this out: x squared plus x plus 2. And that is going to go into the numerator. X to the third plus 2x squared. Okay, there's no x, so I'm going to add in a 0x and minus 1. Okay, 0x is just 0. Plus 0 won't change anything, but it will make it line up. All right, x to the third divided by x squared is just x. Distributing, x times x squared is x to the third. X times x is positive x squared. X times 2 is 2x. All right, we're going to subtract this whole thing, so use parentheses. X to the third minus x to the third is 0. 2x squared minus 1x squared is just 1x squared, or x squared. 0x minus 2x is negative 2x. And we're going to bring down the negative 1. Repeating the process, x squared divided by x squared is positive 1. And really, we can probably just stop right there. All right, let's make sure. 1 times x squared is x squared. 1 times x is 1x. And 1 times 2 is positive 2. All right, there is nothing left to bring down, and we can certainly subtract this if we wanted to, but that would just give us the remainder. All right, once we subtract it, and we said we're going to ignore the remainder. Okay, for the slant asymptote, you don't need it. You don't need the remainder. All right, so this is it right here. The asymptote is going to be y equals x plus 1. All right, it has to be a y equals mx plus b linear equation. Otherwise, it's going to be a curve, and it won't be an asymptote. So that's it right there. You don't need the remainder. All right, so the author's advice when sketching the graph of a rational function that has a slant asymptote: we show the behavior of the graph near the asymptote by plotting points for larger x values. All right, we can tell if the value is large enough by checking its y values in both the line and the function. If they are fairly close, then the x value is large enough. All right, sketch the graph of the rational function. So we're going to start out the same way as we did with the other ones. For the y-intercept, we're just going to use x equals 0. So 0 plus 0 minus 6. Divided by 0 plus 2. All right, the zeros are gone. Negative 6 divided by 2 is negative 3. For the x-intercept, we set the numerator equal to 0. X squared plus x minus 6. Numerator equals 0. How can we solve this? Factor or quadratic? Well, let's see. Let's write out the factors of negative 6. and see if we can find one that adds to positive 1. All right, if we do 3 times negative 2, that would work. So factoring with a 3 and a negative 2, this becomes x plus 3 and x minus 2 equals 0. All right, either one of these can be 0. If x plus 3 equals 0, minus 3 on both sides. And if x minus 2 equals 0, I do plus 2 on both sides. So those are your x-intercepts. The way I wrote it, it makes it look like a line. It's not a line, okay? These are just x-intercepts, so it's really just negative 3 and positive 2. All right, moving along. Vertical asymptote. That's when the denominator equals 0. All right, so if x plus 2 equals 0, minus 2 on both, there you go. All right, for the horizontal asymptote, remember, if the degree of the numerator is greater, then there is none. All right, pretty much, I think all the time, if there is a slant asymptote, there will not be a horizontal asymptote. Okay, and finally, let's do synthetic division here. If we're dividing by x plus 2, for synthetic division, we're going to use negative 2. All right. Coefficients, make sure you count down to 1, 0 on the exponents. The coefficients are 1, 1, and negative 6. All right, bring down the 1. And negative 2 times 1 is negative 2. Adding vertically, 1 minus 2 is negative 1. Negative 2 times negative 1 is 2. All right, the exponent here is a 2. That means the exponent here is a 1. So this is 1x to the first power minus 1. And the remainder is unnecessary. We don't need that. All right, 1x to the first power, that's just x. So the slant asymptote is y equals, this is just x minus 1. All right, so that is your slant asymptote. Y equals x minus 1. You could also use long division if you want, but the synthetic was much easier, and we just ignore the remainder. For the slant asymptote, you don't need the remainder, like we said before. On the graph, y-intercept negative 3, x-intercept negative 3 and 2. All right, so y-intercept, go to the y-axis at negative 3, x-intercept at negative 3 and positive 2. All right, so those are just points, not asymptotes. All right, vertical asymptote, x equals negative 2. And the slant asymptote we said was x minus 1. So x equals negative 2 and y equals x minus 1. All right, x equals negative 2 is right here. And we're just going to draw this in here at x equals negative 2. All right, the asymptote is a dashed line. All right. And the other one we said was y equals x minus 1. So just a basic graph. All right, this is y equals mx plus b, right? So the y-intercept b is at negative 1, And again, this is for the asymptote. This is not the graph. All right, so the y-intercept is at -1. And the slope is just 1. 1 times x, or 1 is your m. All right, so the slope is just 1. So that means up 1, right 1, where you do the reverse. Okay, up 1, right 1, up 1, right 1, where you can go down 1, left 1, down 1, left 1. Okay, and we're drawing a dashed line, as always, for the asymptote anyhow. All right, right through here. And right up here. All right, so that's what we're looking at. And remember, the graph runs along the asymptote, so it'll probably be something like this, and maybe something like that. Let's find out. All right, so I'm thinking maybe we'll plug in -1 and get a point around here somewhere. Let's try that. We'll plug in -1. All right, so I'm just going to make a table here. All right, if we plug in -1, that's going to be 1 minus 1, which is 0, minus 6, so that's -6. Divided by -1 plus 2, which is 1. And -6 over 1 is just -6. So x is -1, y is -6. All right, x is -1, and y is -6. We don't really need to keep going because we can see what happens here. All right, that is going to get closer and closer to the vertical asymptote. Okay, and over here we can plot another point if you want, but we probably don't even need to. I can tell you already it's going to approach the asymptote, but it'll never reach it. All right, let's try x equals 6 and see what happens here. If we plug in x equals 6, 36 plus 6 minus 6, that's going to be 36. And then 6 plus 2 is 8. 36 divided by 8 is what? Instead of 5, that's going to be 4.5, right? 4.5. So at x equals 6, it's at 4.5. All right, x equals 6. Here's 4. Here's 4.5. No surprise there. We knew the function would be approaching the asymptote, but it would never reach it. Okay, so we got half of it. We got half of it, and I'm thinking the other one's going to be similar. All right, here's -3, here's -2. Let's try -2.5 right in here. All right, let's see. I'm going to use the calculator. -2.5. I'm going to plug it in here. Okay, and I get 4.5. All right, so at -2.5, we're at 4.5. All right, so -2.5, we're going up to 4.5. And then let's see, we did -3. Let's see, if we plug in -6, it's probably going to be around here. All right. Actually, let's do, we could do anything right here. Let's do -4. We could do anything in this area. Let's do -4. All right, at -4, we got 16 minus 4, that's 12, minus 6, that's 6. And -4 plus 2 is -2. 6 over -2 is -3. All right, -4 and -3. -4, 1, 2, 3. All right. So this right here, of course, as it goes up, it is approaching this. I'll do it in a different color, actually. As this goes up, it approaches the dashed line. And when this goes down, like I said, you can put one more point down here if you want, but it's just going to approach that asymptote but never reach it. All right, so that is basically it right there. All right, last one. For the y-intercept, you set x equal to 0. We have 0 over 0 minus 1. So, of course, that's 0. And the x-intercept, we set the numerator equal to 0. All right, so x to the third equals 0. And the only way to satisfy that is if x equals 0. So that's your x-intercept. Next up is the vertical asymptote. All right, denominator equals 0, x squared minus 1. If you do plus 1 on both sides and take the square root on both sides, square root of x squared is x, square root of 1 is 1. But when you do square root on both, you need to do plus minus. So the vertical asymptotes are at x equals 1 and negative 1. All right, the horizontal, let's see. If I have room here, yep. The horizontal asymptote, there's none. All right, when the numerator degree is greater than the denominator degree, then there's none. But if it's exactly one more than the denominator, then it's a slant. So we have to do x to the third divided by x squared minus 1. All right, let's see. I could do that here. Do it in a different color. The denominator is x squared minus 1. That gets written out front, and that goes into x to the third. All right, x squared minus 1. And that goes into x to the third. I don't know if it's necessary here, but just to count down, I'm going to... So the exponents count down by 1. I'm going to put the 0x. I don't think it matters. X to the third divided by x squared is just x. And we don't even have to distribute. I mean, you can. X times x squared is x to the third. X times 0 is 0. X times negative 1 is negative x. All right, if you subtract these, you're going to get your remainder, which we do not need. So the equation is just going to be y equals x for the slant asymptote. All right, whatever you get here, the quotient, whatever you get, it's y equals that value for your slant asymptote. You do not need the remainder. You ignore it. That's why I didn't even bother subtracting. All right, there's nothing left to bring down, so that's it. All right, so let's go to the graph. We have a 0 on the y. We have a 0 on the x. So one point is going to be at 0, 0. And then these asymptotes are at x equals 1 and negative 1. All right, so 1 point is at 0, 0. And on the x-axis, we go to 1. And the vertical asymptote is the dashed line that goes through x equals 1. All right, right through there. And then at negative 1, x equals negative 1. Right through the negative 1. All right. So we're in business now. Horizontal, there's none. And the slant is at y equals x. All right, y equals x. That's simple. Whatever x equals, y equals. So at 0, 0, and then 1, 1, 2, 2, 3, 3, 4, 4, and so on. All right, and same with the negatives. For y equals x, whatever x equals, y equals. Negative 3, negative 3, negative 4, negative 4, and so on. Okay, that is going to be a dashed line. Okay, and now we have to plot a few points here. All right, this one is a little bit of a pain in the neck. All right, you need points to the left and right of the vertical asymptote. Let's try x equals 2 and x equals negative 2. That should be pretty simple at least. All right, for the xy. X equals 2 and negative 2. We have 8 over 4 minus 1, so that's 8/3. And 8/3 is basically what? 2 2/3. All right, and for negative 2, it's going to be negative 8 over 4 minus 1, which is 3. So negative 8/3. And that's going to be negative 2 2/3. All right, I can't fit it here, but it's going to be the negative of 2 2/3. 2 is at 2 2/3. All right, so 2, x equals 2 is at 2 2/3 right there. And negative 2 is at negative 2 2/3. Negative 2 is at negative 2 2/3 is right there. All right, let's see. I'm pretty sure it's going to be a curve in here. Let's try it at negative 6. All right, at x equals negative 6. I'm going to use the calculator. And I got exactly negative 7. Okay, make sure you can do something like that on the calculator. Plug in negative 6 for x. If you need help, let me know. But at negative 6... it's going to be y equals negative 7. Okay, and just to make sure, it's probably going to curve down here, but let's try negative 1.5. All right, I know it's a pain in the neck, but just to be accurate, plug that in right here, and I get negative 2.7. All right, so let's see. Shoot. The negative 2 was at 2 2/3. That's actually 2.67. All right, and this was negative 2.67. Now we're at negative 2.7. So it's going down. It's getting more and more negative. This was at negative 2. And this is at negative 1.5. So the negative 2.7 is lower than negative 2.67. All right, so at the negative 1.5, it is getting lower. Okay, just barely. But we can tell it's getting lower and lower what direction it's heading in. So that's all we need. So this here is basically like that. All right, it's approaching the asymptote. And inside here, let's see. Let's try right here. Right here would be negative 1/2. All right, so let's try that. -1/2 or -0.5. I'm going to plug that in. All right, I get a very small number, 0.167, but at least we know it's greater than 0. At -0.5, it's headed up. So we got that right there. And then let's try on the other side, 0.5. Calculator again. All right, and that's -1.67, close to 0, but it's headed down. So that's at 0.5 or 1/2. So right here, it's headed down. Okay, so we can keep plotting the points, but we can see right here, it is heading up. All right, I'm going to have to thin this out. Okay, right here, it is heading up. All right, this is difficult to draw here, but it is heading up. And of course, it's getting closer and closer to that asymptote, but it never reaches it, okay? And over here, it's headed down. So it just keeps getting closer and closer, but never reaches it. All right, and finally, we got this part here. All right, this should be easy. We got 2 here. We can plug in something larger. We can plug in like x = 6 if we want to see if it goes this way. All right, so real quick, let me see. I didn't use 6 yet. I used -6. It's probably going to be just +7, right? If I plug in 6, right here on the calculator. All right, and rounding off, I get 6.2. So at x = 6, it's 6.2. All right, at x = 6, it's going to be y = 6.2. So that makes perfect sense. And let's see, right in here, let's try 1.5 and make sure it's going up. I'm almost positive it is. It's probably going to be +2.7, right? 1.5. Plug that in. Yes, I get +2.7 at 1.5. All right, so at 1.5, I'm going to go up to 2.7. And let's see, what was this point at 2? That was 2.67, and this is 2.7. All right, so it is going up. It is going up, and right here, it basically turns around like so. It approaches the asymptote, but never reaches it. All right, pain in the neck, but that's basically it right there. I think the -6, I made a tiny mistake. 6 was 6.2. I bet you -6 would be -6.2. This is probably a mistake. Yes, this right here was supposed to be -6.2. I don't think it's going to make a difference. At -6, it was down here anyway. Okay, so that's it basically. There's your graph. All right, 3 pieces to it. This right here, this right here, and this right here. You basically have to plot points to see how it approaches the asymptote. But once you get going in a certain direction, you know that the graph is just going to approach but never reach the asymptote. All right, so that's basically it right there. Pain in the neck, but that's it.